Now what we want to do is learn the rules of the quantum numbers that are produced by the Schrödinger equation. These are called wave function, and it's just a calculation that calculates the probability of finding an electron at any particular place with any particular energy. Remembering that we can never know exactly the position or the momentum of the electron simultaneously, because the more we know about the position, the less we know about the momentum, and vice versa. So the solutions to the Schrödinger equation give us the quantum numbers. And the quantum numbers that we're going to explore start with n. They are n, l, and m sub l, the magnetic quantum number. So the first quantum number is the principal quantum number. The principal quantum number describes the overall energy level of the electron, or if you will, the distance from the nucleus. So if I have a positively charged nucleus and then I have a negatively charged electron that's in what we call an orbital at some distance from the nucleus. And so we might call this, since this is the n principal quantum number, we might call this electron existing in an orbital at n equals 1 distance or energy level from the nucleus. And then we might have another electron at another discrete whole number, integer, n equals 2 distance from the nucleus. Keeping in mind that we can never have n equals 1.5, and we can't have n equals 0, because if n equals 0, the electron is actually in the nucleus. So the rules for the n principal quantum number are that they can have positive integral values of 1, 2, 3, 4, 5, 6, and 7. 7's all we'll need for our periodic table, but they could literally go out to infinity. So you need to remember the rule for the principal quantum number, and that is n. The principal quantum number can have values of 1, 2, 3, and 4. And we go on to L, the azimuthal quantum number. Now, the azimuthal quantum number describes the shape of the orbital in which the electron resides. So we have a number of different shapes, but the azimuthal quantum number describes the shape of the orbital. The integral values for the L quantum number are 0, 1, 2, 3, 4, all the way up to a maximum value of n minus 1. So what this means is if our n value, our n principal quantum number, was 5, then the maximum L value for an n value of 5 would be 4. And that's because 5 minus 1 is equal to 4. So that tells us what the maximum L value is. Can you guess? If the n value were equal to 2, what would be the maximum L value that was permitted? Well, we could have 0, we could have 1, but that's the maximum value that we could have, because the L value can only go up to a maximum value of n minus 1, and 2 minus 1 is equal to 1, and so 1 would be the maximum L value. Now we come to the magnetic quantum number, or m sub L. And the m sub L value, this is actually the orbital itself. This is where the electrons live. They live in orbitals, and the orbitals are represented by the m sub L value. The m sub L value describes the orientation of the orbital in space in which the electron resides. The possible values for the m sub L value depend on the L value. And so an m sub L value can have a value of minus L through 0 all the way up to plus L. So for instance, if the L value were equal to 1, that's the L value, then you could have m sub L values that were equal to -1, 0, and +1. That's because the L value is 1, and we can go from -L through 0 to +L. Those are all possible values for an L value of 1. So if I had an L value, let's say, of 3. So here I have an L value of 3. My possible M sub L value could be -3, -2, -1, 0, +1, +2, and +3. Now, I need you to understand, these values are not numbers that we're going to add up. These are addresses. We're simply finding the probable address of an electron. So we're going to wind up with addresses that look like this, where we've got an N value, let's say, of 3. We've got an L value, let's say 1, and then we have an M sub L value of -1, and then we have one other possible quantum number, which is what we call the spin quantum number, which I'll tell you about in a moment, and that can either be +1/2 or -1/2. So N, L, M sub L, and M sub S. Let's talk briefly about terminology. The electron shell is simply the collection of orbitals with the same value of N. So for instance, an electron shell could be a shell N equals 3. So all the M sub L values, because you remember the M sub L values, those are the orbitals. And so all the orbitals that have the same value of N, they're all in the same electron shell. Now, an electron subshell is a little bit more specific. You have a collection of orbitals, and remember, orbitals are M sub L values, and all those M sub L values will have the same value of N and the same value of L. So for instance, let's say we have an N value that equals to 3, and we have an L value within that N value of 3 that's equal to 2. The M sub L values, which would be in the subshell, that is N equals 3 and L equals 2, those M sub L orbitals would be -2, -1, 0, +1, and +2. All of these orbitals are in the same subshell because they have the same N value of 3 and the same L value of 2. And remember, the rules for the M sub L values, it can be -L to +L. Since L is 2, we can have -2, -1, 0, +1, and +2. 5 different orbitals for an L equals 2 subshell. So let's look at that a little bit more closely. Here I have an N value of 1. Now, if you remember, having an N value of 1, the maximum L value I'll be able to have for N equals 1 is L equals 0. That's because the maximum L value goes up to N minus 1, and 1 minus 1 is 0. So that's going to be my maximum L value. M sub L value has to be 0 because the rules for M sub L are -L through 0 to +L. Well, if L is 0, the maximum M sub L value has to be 0 as well. So for N equals 1, I only have one orbital and one subshell. For N equals 2, I have a different situation. Here I can have an L value of 0 because if N equals 2, I can go from, the rules are for L values 0, 1, all the way up to N minus 1. Well, here's the N value of 2. 2 minus 1 is 1, so the maximum L value I can have for N equals 2 is L equals 1. Now, here I've got M sub L values that have N equals 2 and L equals 0, and I have 3 more M sub L values that have N equals 2 and L equals 1. That represents 2 different subshells, although all of these orbitals, all these m sub L values are in the same electron shell. They're simply in different subshells. If I have n equals 3, I can have an L value of 0, an L value of 1, and an L value of 2, because the maximum L value I'm permitted for n equals 3 is 3 minus 1, which is 2, which means that I can have m sub L values for L equals 2 of minus 2, minus 1, 0, plus 1, or plus 2. For n equals 3 and L equals 1, I can have m sub L values of minus 1, 0, and plus 1. This is an entirely different subshell, but can you see that all of these orbitals, and remember, the m sub L values are the orbitals, all of these orbitals are in the same electron shell. They are simply in different subshells. Shapes of orbitals. The shapes of orbitals are determined by the L value. The L value, if you remember, is the azimuthal quantum number. And by definition, the L value equal to 0 is what we call an S orbital. L equals 1 is a p orbital. L equals 2 is a d orbital, and L equals 3 is an f orbital. All four of these orbitals have different shapes. L equals 0, L equals 1, L equals 2, and L equals 3. Let's try it. There's just four letters, S, P, D, F, and it goes right down 0, 1, 2, 3, S, P, D, F. Let's take a look at their shapes. The s orbital is shaped like a sphere. So this 1 that you see here is representing the n value 1. And the n value 1 can only have an s orbital because it can only have an L value of 0, and L equals 0 is by definition an s orbital. So this is the 1s orbital. It's spherical. There's only one type of those. However, if you go further out from the nucleus, you can also have a 2s orbital, and that's simply a larger sphere. So this would be n equals 2 and L equals 0, and then you'd have a 3s orbital, and there'll be an s orbital for every n value. And then we have the p orbital. The p orbital is shaped like a dumbbell. If you remember, L equals 1 is equal to a p orbital. So L equals 1 is a p orbital, and if L equals 1, we can have m sub L values of minus 1, 0, or plus 1. There are 3 orbitals for L equals 1, and that's a p orbital. So what that means is there are 3 types of p orbitals. If you take a look at the dumbbell shape that you see here, it's on the 3 different axes in a 3-dimensional coordinate system of x, y, and z, and these orbitals are labeled the pz, the px, and the py for that very reason. These are not really hard spheres. It's just a representation that's easy to be drawn. What would be more accurate is this representation of the p orbital. Each pixel in this picture represents a solution to the Schrodinger equation, and when you compile all those solutions for the probability of finding an electron in any particular place at any particular time, because remember, we can never know both the position and the momentum of an electron simultaneously, only the probability. And so what we have is a probability map. We simply use this representation because it's easier to draw. What we normally call this is the electron cloud. 3 different types of L equals 1, which are p orbitals. The d orbital. The d orbital is shaped like a double dumbbell. If you remember, L equals 2 is a d orbital. And if L equals 2, we can have m sub L values of minus 2, minus 1, 0, plus 1, or plus 2. That's 5 different orbitals in a d subshell. And here's the shapes that the Schrodinger equation predicts for a d orbital. You have this double-lobed dumbbell. Now keep in mind, this is one orbital, as this is one orbital, and this is one orbital, and this is one orbital. And then you have this odd-looking donut shape, the pacifier-looking thing, which is the 5th solution to the Schrodinger equation. And this is all one d orbital. Here's the f orbital, very complex shape. And you can see many lobes. It just drives you crazy looking at F orbitals. So if you remember, the L value for F is L equals 3. And if L equals 3, these are the possible M sub L values: -3, -2, -1, 0, +1, +2, or +3, going from -L to +L. And that is 7 different possible orientations, or orbitals rather, for the F subshells. One more orbital. The Pauli exclusion principle does not come from the Schrodinger equation. What it says is that no two electrons in an atom can have the same set of 4 quantum numbers, N, L, M sub L, and M sub S. It would be as if you were trying to occupy the same space as your roommate, the exact same space. So you need your own room. And so we give the electrons their own room. Now, there are only 2 electrons permitted to occupy any single orbital. What we do to separate them from each other is we give them a spin number of either +0.5 or -0.5. So and this is called spin up or spin down. We call that the spin quantum number. That is the 4th quantum number, the only one that doesn't come from the Schrodinger equation. But we can only put, according to the Pauli exclusion principle, 2 electrons in a single orbital. So I picked the 1s orbital for helium. It only has 2 electrons. And if we start out with the first 3 quantum numbers, N, L, and M sub L, we see that both of our electrons have exactly the same address. And that's what this represents. It's just an address. But if we take one electron and spin it one direction and the other electron and spin it the other direction, we now have a 4th quantum number, which gives each of our electrons a unique address. Let's talk about Hunds Rule. Degenerate in this context means the same energy level. For degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. So that sounds a little bit confusing. Let me show you what I mean. For instance, these orbitals, these 3 2p orbitals, are all at the same position. If I were to draw a straight line from the y-axis, which indicates the energy level, you would find that they're at the same location horizontally, indicating that they are degenerate. They're at the same energy level. And what Hunds Rule says, that you can reach the lowest energy when the number of electrons with the same spin is maximized. Well, remember, everything wants to be at the lowest possible energy. It's the natural flow of things. Water flows downhill. Electrons want to be at their lowest energy level, and they will be unless acted upon by some other force. Here's the way it works. The first electrons to come into a set of orbitals will go to the bottom, and that makes sense. You fall as far as you can go until you meet some immovable force. The first 2 electrons will land in the first orbital. One will be spin up, one will be spin down. If you have one spin up and the other spin up, you violated the Pauli exclusion principle, because you can only have 2 electrons in every orbital. One has to be spin up, one has to be spin down. Here come our next 2 electrons, one spin up, one spin down. We've obeyed the Pauli exclusion principle. Here's what Hunds Rule says. It says that this orbital right here is at the same energy level as this orbital over here where we put our first electron, and that the lowest energy is going to be obtained by putting the next electron in the degenerate or the adjacent orbital that's at the same energy level, spin up with the same spin. That's Hunds Rule. And the next electron would go in the next degenerate orbital, and it would also be spin up. Now the electrons are forced to pair, and so the next electron goes in spin down in one of those orbitals, and so on till we get this configuration, which is very stable, where we have a filled shell. What we have here is the electron configuration of neon, and we know neon is a noble gas. It doesn't like to react. Here's a clicker question. Which of the following sets of quantum numbers, N, L, M sub L, and M sub S, is possible? What you have to do to get this correct is to follow the rules for quantum numbers. Now remember, N values can only be positive integers, 1, 2, 3, 4, 5, 6, and so on. L values can be 0 all the way up to a maximum of n minus 1. M sub L can only be minus L through 0 to plus L, and it can be any of those. M sub S can only be minus a half and plus a half. So let's go ahead and let's solve our problem according to the rules of quantum numbers. Let's take a look. First of all, let's look at the value for n in answer A. Now, what do the rules say about n values? Well, the rules say that n can only be positive integers. And so n can't be 0, so we know that this breaks a rule of the n quantum numbers. It can't be 0, so this is not the answer. Let's take a look at B. 1 is a possible n quantum number. That's a good value for n. And if n is 1, can L be 0? Let's look up. And what we see for L is that the rule says L can be 0, 1, 2, 3, all the way up to a maximum value of n minus 1. Well, if n is equal to 1, 1 minus 1 is equal to 0, and so L equals 0 when n minus 1 is just fine. Let's take a look at the M sub L value. If we look at M sub L, it can be minus L through 0 to plus L. So if we look at that, L is 0, so the only possible value for M sub L is 0. So that is just fine, and so the first three quantum numbers are okay. Now, the M sub S value can only be plus a half or minus a half. This could have been plus a half. It is minus a half, so that's okay. That makes B the answer to our problem. Let's take a look and see what's wrong with C and D. N can be 1 according to the quantum rules. If n is 1, L can be 0. But if L is 0, the maximum M sub L value comes from this rule, minus L through 0 to plus L. Well, if L is 0, then there is only one possible value for M sub L, and that's going to be 0. So that breaks a rule. Here we have n equals 1, L equals 0. That's fine. We can have M sub L equals 0 if L equals 0, but we can't have minus 1 for the M sub S value. So hopefully that will help you work through that kind of problem. All you have to do is follow the quantum rules. I want you to remember that L equals 0 is an S orbital. L equals 1 is a P orbital. L equals 2 is a D orbital. L equals 3 is an F orbital. S is a sphere shape. P is a dumbbell shape. And D is a double dumbbell shape. And then F is, it's crazy, man. It is one wild dude.